Hey everyone! So in this video I like to talk about the graphs of tangent and the reciprocal trigonometric functions secant, cosecant, and cotangent. So we've already talked about graphing transformations of sine and cosine, and in a moment we'll talk about graphing tangent. And these three will probably be more important or will come up more frequently than the graphs of the reciprocal trigonometric function. And so we're going to talk about them just for the sake of completeness, but really if you have anything to focus on, really focus on the graphs of our main three trigonometric functions. Okay, so if I have the function f of theta is equal to tangent of theta, the way we frequently think about tangent of theta is sine of theta divided by cosine of theta. And we said in the past that one interpretation for tangent of theta is the slope of the angle theta. And so here, just to really make that very clear, is if we have some angle theta, and maybe it corresponds to this point out here. And so here's my angle theta. Then if we're looking at the unit circle, right, the x-coordinate of this point and the y-coordinate of this point really correspond to the values of sine of theta and cosine of theta. So here, this is the distance corresponding to sine of theta, and this is the distance corresponding to cosine of theta, right? That x-coordinate and that y-coordinate are cosine of theta and sine of theta respectively. And well, if we look at the slope of that line, right, if we imagine sort of extending this line out, right, well, the change in y is exactly that sine of theta value, and the change in x is exactly that cosine of theta value, and so we can view tangent, sine of theta divided by cosine of theta, as the slope of this line. And so this is a pretty useful way of thinking about tangent, and it gives us some nice intuition. Another thing to take away from this picture we've drawn here is that, well, if we imagine going another pi radians around this unit circle, right, so here this angle is theta plus pi, well, that angle is going to have the same slope, right? It's going to correspond to the same line. And so one thing to really notice is that, here maybe I'll write it down as this, that tangent of theta is going to be equal to tangent of theta plus pi. And really what this is saying is that the period of tangent is pi. Right, it repeats itself. It only takes going halfway across this unit circle for tangent to repeat itself, for its outputs, for its values to repeat itself. Another thing to keep in mind is that tangent is a fraction. Right, so tangent is a fraction. We see that above. It's sine of theta divided by cosine of theta. And so there are times where it could be undefined. Right? When we have division by 0 is when a fraction is undefined. So it's undefined when the denominator is 0, and because tangent of theta is sine of theta divided by cosine of theta, this is exactly when cosine of theta is equal to 0. And so when is cosine of theta equal to 0? Well, here, let's draw a picture for that. If I have my unit circle, right, cosine of theta corresponds to the x-coordinate of the points on the unit circle. And so when do we have the x-coordinate for a point on the unit circle equal to 0? Well, that happens exactly here and here. Right? This is the point 0, 1, and this is the point 0, -1. And so because cosine of theta is exactly this x value, these are the points corresponding to when cosine of theta is equal to 0. And so the angles are any angles that bring us to these points, right? So here, you can imagine pi over 2 bringing us to have cosine of theta be equal to 0, then if I add another pi, right, so 3 pi over 2, we also get cosine of theta is equal to 0. In other words, a place where tangent of theta is undefined. And I can go around another pi back to the top coordinate, or the top point, and then another pi to go back to the bottom point. And so here we see that cosine of theta is 0. For pi, pi over 2, 3 pi over 2, 5 pi over 2, and so on and so on and so on. Or in other words, really for pi over 2 plus pi times n. And here when I say times n, I'm talking about some integer number, some whole value, could be positive, could be negative. Right, a whole number multiples of pi added on to pi over 2 will make our cosine value, cosine of that angle equal to 0. In other words, it's going to make the denominator of sine of theta over cosine of theta equal to 0. And that's going to mean that tangent is undefined for such an angle. And so here, these are the angles that make the denominator equal to 0 for tangent of theta. And so the domain of tangent of theta, well, this is, it's going to be, all values are going to be okay except for the values of pi over 2 plus pi times n for a whole number of values of n. Right, and this kind of makes sense with this idea of tangent of theta being the slope of our angle. Right, here these two, or all of these angles correspond to a vertical line, an undefined slope. Okay, so let's go ahead and graph this function, tangent of theta. F of theta is equal to tangent of theta. And so we said that it's going to be undefined for pi over 2 and any multiples of pi added on to pi over 2, right? So here 3 pi over 2, negative pi over 2, and so on and so on. But to get a better sense of how we can graph this, let's go ahead and make a table. So here this is going to be theta, it's going to be f of theta, or tangent of theta. Now if we plug in 0, right, so tangent of theta corresponds to sine of theta over cosine of theta, or sine of 0 over cosine of 0 in this case. And sine of 0 is 1. Sine of 0 is 0, cosine of 0 is 1. So this comes out to be 0, and it makes sense, right? On the unit circle, maybe I'll have a unit circle just drawn out here for us to sort of refer back to. If we look at an angle of theta equal to 0, well, the slope of this line, the slope of this angle is going to be 0, right? So tangent of 0 is 0. If we have pi over 6, we get sine of pi over 6 over cosine of pi over 6. Well, sine of pi over 6, that's the horizontal, sorry, not the horizontal, that's the vertical coordinate for this point. That's 1/2. And so we have 1/2 divided by, and then cosine of theta is the horizontal coordinate for that point, and so we get the square root of 3 over 2. And so I can multiply the top and bottom of this fraction by 2. And so I get 1 over the square root of 3 is our tangent of pi over 6. What about pi over 4? Well, here pi over 4 corresponds to sort of this nice 45-degree angle. And so the slope of this is 1, but we can see this by noticing that sine of pi over 4 divided by cosine of pi over 4. Right, this is equal to the square root of 2 over 2 divided by the square root of 2 over 2, or just 1. Right, but we can kind of see that this would correspond to a 45, 45, 90 triangle, an isosceles triangle with the same leg lengths. And so if I take the ratio of those leg lengths, I'm going to get 1. This is a slope of 1. Okay, and then pi over 3. It's kind of like our pi over 6 computation, but in reverse, right? So sine of pi over 3 divided by cosine of pi over 3. This is the square root of 3 over 2, right? That's the y value of our 30, 60, 90 triangle fit into this picture here, this point here. And then cosine of pi over 3, that's 1/2. And then multiplying the top and the bottom by 2 gives us the square root of 3. Right, so tangent of pi over 3 is the square root of 3. And it kind of makes sense that here the tangent of pi over 3 is going to be larger than tangent of pi over 6, right? The square root of 3 is larger than 1 over the square root of 3. And that's, we have a steeper angle for tangent of pi over 3. And so it ought to be larger. And then here, let's do another one, pi over 2. Maybe I should put it down a little lower. So pi over 2. Right, so here we have sine of pi over 2, cosine of pi over 2. Sine of pi over 2 is, what is that? That's 1. Cosine of pi over 2 is 0. And like we said earlier, here this brings us to a denominator of 0. We get an undefined result. Okay, and then so I think we ought to do a few more just to really paint the full picture here. But I think it won't be much more before we can really graph this function out. So here, the next angle I want to try is 2 pi over 3. We have sine of 2 pi over 3 divided by cosine of 2 pi over 3. So we've got this angle out here, corresponding to another 30, 60, 90 triangle where the height is square root of 3 over 2. Cosine of 2 pi over 3, though, comes out to be negative 1/2 because we're looking at the left side of the unit circle. So this is negative square root of 3, right? If I multiply the top and the bottom by 2, I still have the same fraction, just kind of express it more nicely as the negative square root of 3. Here, 3 pi over 4, another 45-degree angle sort of floating around in this picture. We have a slope of negative 1. Where we get square root of 2 over 2 divided by negative square root of 2 over 2, so this is negative 1. 5 pi over 6. This comes out to be negative 1 over the square root of 3. And it's very similar to our computation earlier for pi over 6, and then here if I plug in pi, we get sine of pi is 0 divided by cosine of pi. Well, cosine of pi is negative 1. So we get 0 over negative 1, but either way, that's still 0. Right, so here, I get a flatter angle, and then one last one for our horizontal angle. Okay, and so really that gives us a lot of information about this tangent function, and because tangent has a period of pi, we really told the full story. If we look across the unit circle from these angles, we'll get the same results. So here, let's go ahead and plot these points out. So here, if I have an angle of 0, right, theta or input is equal to 0, we get an output of 0. If I have pi over 6, we get 1 over the square root of 3. So the square root of 3, that's some number short of 2. So 1 divided by something just shy of 2 gives me maybe some value out here. Pi over 4, I get 1, a slope of 1. Pi over 3, I get a slope of the square root of 3, so further up here. And as I start plugging in larger and larger values of our angle theta, as we approach pi over 2, well, our line is going to get steeper and steeper and steeper, right? So here, if I get closer and closer to this angle of pi over 2, I get a much more vertical line, but I want to emphasize that this vertical line would have a positive slope, right? As long as it's just shy of pi over 2, right before pi over 2. And so really this slope here would really explode upwards. The value of tangent of theta would really increase and skyrocket upwards as we get near pi over 2. And then once we exceed pi over 2, we still have a really steep slope, but then it'll be negative, right? Here, if I kind of draw an angle just past pi over 2, the slope is still very steep, but it's steep and negative, and so I'd imagine getting output values way down here. Right, and then what do we get next when I plug in 2 pi over 3? Well, we get negative the square root of 3, so some number that's just a little bit larger than negative 1 or more negative than negative 1, and so here this is maybe out here. Square or 3 pi over 4 gives us just negative 1. 5 pi over 6 would be negative 1 over the square root of 3. That would be out here. Plugging in pi, we get 0. And then our output values would start to repeat, right? So I get something like this, this, and this. We kind of see that this picture here would look something like, oops. Would look something like this. Right, and again we see that period of pi, it repeats itself every pi units, but really, between intervals of, or between negative pi over 2 and pi over 2, pi over 2 and 3 pi over 2, and so on and so on. So that's a rough picture of the graph of our tangent function. Usually we'll be focused on one period, that period between negative pi over 2 and pi over 2. So really this one here. But it's a good sense to have this entire picture in your head. So we've talked about how tangent represents the slope of our angle. This also lets us know that the range of tangent, so we already talked about the domain, it's everything but pi over 2 plus pi n. The range, on the other hand, we can see that it goes upwards forever and downwards forever. It has a range of negative infinity to positive infinity. Right, because our slopes of our angle can get as steep as we want in the positive direction, as steep as we want in the negative direction. We can get all values for our slope. And so that tells us that the range of tangent is negative infinity to positive infinity. So another thing I want to bring up is something we brought up for sine and cosine. So we noticed that for sine of theta, actually maybe let me write it like this. So sine of theta is an odd function, and cosine of theta is an even function. And so what did this mean? Well, this just meant that if I plug in negative theta, so negative of some angle into sine of theta, well, that just amounts to us getting the negative of the output if I were to plug in theta into my sine function. And our cosine function, if we plug in the negative of some angle, it's really equivalent to plugging in the positive of that angle. Right, so here, cosine of theta really doesn't care about negating an input, whereas sine of theta does. So we called sine of theta, we called this odd, and we called cosine of theta even. And one way we can interpret a function being even is that it's symmetric about the vertical axis, whereas a function is odd if it's symmetric about the origin. And so if I look at the graph of my tangent function above, well, it's not symmetric about the vertical axis, right? If I reflect my graph over this line here, I don't get the same picture, I don't get the same graph, and so that's telling us that this function is not an even function. If I plug in negative of some angle, I'm not going to get the same result for my tangent function as if I were to plug in that angle without negating it. And it's no guarantee that the function's odd either, but it turns out to be the case. So here, tangent of theta tangent of negative theta is equal to negative tangent of theta. It is also an odd function. And so let's prove this. Right, so if I have tangent of negative theta, and I want to prove this by showing that at the end of the data, or at the end of the day, we're going to get negative tangent of theta out. So tangent of negative theta, this is the same as sine of negative theta divided by cosine of negative theta, right? Tangent of an angle is the same as sine of that angle divided by cosine of that angle. And so here it's the same as sine of negative theta divided by cosine of negative theta. But because sine is an odd function, I can sort of pull out that negative factor here, and I'm just left with negative sine of theta in the numerator. And because cosine is an even function, we can kind of forget about this negative factor here. And so here, this is really the same as cosine of theta in the denominator without that negative sign, because cosine is an even function. And so here really, this is my tangent function, but just with an extra negative sign here. And so this is the same as negative tangent of theta as we wanted to show. So tangent of theta is an odd function. Okay, so next up I want to talk about our secant of theta function. F of theta is equal to secant of theta. And recall that secant of theta is this reciprocal trigonometric function to our cosine function, 1 over cosine of theta. And so cosine has a period, right? Cosine of theta has a period of 2 pi. And so secant of theta is going to have that same period as well, right? Secant of theta is 1 over cosine of theta, and so it's going to repeat its values when cosine of theta repeats its values. So every 2 pi. So secant of theta has a period of 2 pi also. Tangent, like tangent of theta, secant of theta, it also consists of having cosine of theta in the denominator. And so we get that secant of theta is undefined when cosine of theta is 0. Maybe I won't put that dash there to make it look like negative secant of theta. So secant of theta is undefined when cosine of theta is equal to 0. And so this occurs, like we said earlier, at pi over 2. And any time we add on pi multiples to pi over 2, right? So here, anytime we're at the top of the unit circle, at the bottom of our unit circle from this angle of theta, we get cosine of theta is equal to 0, and so secant of theta is going to be undefined. And so this tells us that the domain of our secant of theta function, well, this is for all values of theta not equal to these angles that result in cosine of theta being 0. So pi over 2 plus pi n, where n is some whole number, some integer. These are the values of theta that we want to exclude from the domain, right? So really everything else is fair game to plug into our secant of theta except for these values here. Another thing that I think is going to help us with graphing our secant of theta function, our reciprocal function, is to sort of pay attention to one idea, that dividing dividing by a number less than 1 is going to make whatever number you're dividing larger, right? So dividing a number by another number less than 1. Right, so near 0, some small number results in a larger quantity. Right, maybe just to give some explicit examples, if I take 20 and I divide it by 0.01, in other words, if I have $20 and I want to ask how many pennies go into $20, well, there's 2,000 pennies that fit into $20. Right, so dividing 20 by 0.01 makes our result pretty large. And if I make that divide, or the denominator smaller, if I have something like 0.001, well, this number only gets larger. I can fit more of this very, very small quantity into my numerator. I get 20,000 out in this case. Right, the idea here is that this denominator goes into our numerator many times over. And so we're going to get a large result. Okay, so let's go ahead and graph our function f of theta is equal to secant of theta. In other words, 1 over cosine of theta. I think it's going to help us out to graph this cosine function first, actually, just to give us some context. So in some sense, cosine of theta starts at 1, right? If I plug in 0 for cosine, I get 1 out. Plugging in pi over 2 gives me 0, pi gives me -1, 3 pi over 2 gives us 0, and then 2 pi gives us +1 again. And then cosine begins to repeat itself. And so here's one period of our function, cosine of theta. And then what about secant of theta? Well, here, we get division by 0 wherever cosine of theta is 0. And so those give us undefined results from our secant function. And so we don't expect outputs there. Right, so pi over 2, 5, or 3 pi over 2, 5 pi over 2, and so on, our secant function is undefined. And so here, let's go ahead and make a table for our secant function. So if I plug in 0 into our secant function, that's 1 over cosine of 0. In other words, 1 over 1. If I plug in pi over 6, this is 1 over cosine of pi over 6. Well, this is 1 over, cosine of pi over 6 is the square root of 3 over 2. And when we divide by this fraction, right, it just takes the reciprocal of it. Right, it multiplies by the reciprocal of that square root of 3 over 2 to divide it. And so that's the same as 2 over the square root of 3. And so if I plug in pi over 4, we get 1 over cosine of pi over 4. This is 1 over the square root of 2 over 2. And again, dividing by that fraction is the same as multiplying by the reciprocal. And so this is 2 over the square root of 2. I plug in pi over 3. And this is 1 over cosine of pi over 3 or another. It's the reciprocal. You have cosine of pi over 3. And cosine of pi over 3 is 1/2. This gives us 2. And then if I try to plug in pi over 2, well, we get an undefined result, right? We get division by 0 because cosine of pi over 2 is 0. Here, so I'll use orange to graph this function secant of theta. So I get 1.0, 1 for secant of theta, just like my function cosine of theta. If I plug in pi over 6, we get 2 over the square root of 3, and the square root of 3 is just shy of 2. And so this is some number pretty close to 1, just a little bit more. And here for pi over 4, we get 2 over the square root of 2, and the square root of 2 is a little bit smaller, and so dividing by that will give us a slightly larger result. And then plugging in pi over 3 is going to give us 2 out. And you can kind of see as we get closer and closer to pi over 2, we get larger and larger values. And that's because here cosine of pi over 2, cosine of numbers closer and closer to pi over 2 are smaller, and dividing by smaller and smaller numbers is going to give us larger values. And so we can kind of apply the same idea, the same reasoning to sort of the next part of our secant function. Right? Here I can see that cosine of pi is going to give me -1. And so secant of pi is going to give me -1 as well, right? 1 over -1 is still -1. But away from this point, cosine is getting smaller and smaller and smaller, and so dividing by that quantity is going to make my result at least more and more negative. It's going to make it larger and larger negative, and as we get closer to pi over 2 from this side, our values are going to start to skyrocket, right? Dividing by that number really, really close to 0, that cosine gives us, is going to make our values larger and larger and larger. But we're dealing with a negative quantity here, and so it's going to be a really, really large negative amount, right? Cosine of such an angle is going to give me a negative result, and so secant of that angle is also going to give me a negative result. And similarly on this side, right? So as we get closer and closer to 3 pi over 2, cosine of that angle is going to be smaller, and dividing by that result is going to make my secant of theta value get larger and larger and larger. And similarly, secant of 2 pi is going to give me 1, just like cosine of 2 pi gives you 1. And as we sort of move away from this point towards 3 pi over 2, we're dividing by some small amount from cosine of theta, and so that's going to make our values get larger and larger and larger. And so really this is sort of the shape of our secant function, and it really repeats itself in this way, but it can pretty much be built from our cosine graph. Right? And one thing I want to point out here is that right, because cosine of theta falls between -1 and 1, dividing by this quantity is going to make our results larger, and so we're never going to get any value from a secant of theta between -1 and 1, right? Because we're always dividing by some small quantity that's going to make our result larger. And so here, the range of our secant function, it's everything outside of this window from -1 to 1. In other words, here it's negative infinity to -1, as well as 1 to positive infinity. So negative infinity to -1 union 1 to positive infinity. Okay, so let's go ahead and apply our same reasoning to our cosecant function. So here, if I have g of theta is equal to cosecant of theta, this is the same as 1 over sine of theta. And so the domain of this function, the domain of cosecant of theta, this is all the values of theta except for the ones that lead to sine of theta being 0, right? For us to get division by 0 that we want to sort of exclude. And so when is sine of theta equal to 0? What are the values that we want to remove from the domain here? Well, if we look at the unit circle, right, sine of theta is the y coordinate on the unit circle, and that y coordinate is 0 at this point here and at this point here. In other words, an angle of 0, pi, 2 pi, 3 pi, 4 pi, really just any multiple, whole number multiples, integer values, multiples of pi. Okay, so integer just means whole number, positive or negative. And so here we see that I get these sort of vertical asymptotes at 0. What is this? This is pi and 2 pi and so on and so on. And then also, I think it can help us again to have the graph of our base function sine of theta here. So here, let me graph sine of theta. We know that we get pi over 2 gives us an output of 1. Pi gives us an output of 0. 3 pi over 2 gives us an output of -1, and 2 pi gives us an output of 0, right? So our graph of our sine function looks something like this. And then it repeats itself. Okay, so similarly to our secant function, right, here we're going to get 1 from our cosecant function when sine of theta is equal to 1. So here I see this point. is going to also be on my cosecant function, the graph of my cosecant function. And as sine gets smaller and we start dividing by by smaller values, our results are going to get larger, right? Dividing by some small number is going to make our results larger. And so here we can see that as sine of theta gets closer to 0, cosine of theta is going to skyrocket. And similarly out here, when sine of theta is equal to -1, well, that's going to make cosecant of theta -1 as well. But as we move away from this point and sine gets smaller, dividing by that smaller number is going to make cosecant get larger, at least in the negative direction. And so we similarly get this sort of U-shaped graphs pointing upwards and downwards. Or actually, no, this should be the other way around. This should be down here. And so similarly to our secant function, the range for our cosecant function, well, we can see here that dividing by sine of theta is always going to make the results larger than 1 or smaller than -1, like more negative than -1. And so here we get values or outputs from -infinity to -1, union 1 to infinity. Okay, so here, that's really most of what I want you to see for our secant function and our cosecant function. These things aren't things I'm expecting you to memorize, but I do want you to have seen them, know how to reconstruct them, know the ideas for how to graph these functions. And also, actually knowing their domains is pretty important. That is something I do want you to have in mind and to remember, or at least know how to find. Okay, so let's go ahead and figure out one last graph, the graph of our cotangent function. F of theta is equal to cotangent of theta. And so this is the reciprocal of our tangent function. In other words, it's going to be cosine of theta over sine of theta. And so our domain is going to be everything except for values of theta that lead to sine of theta being 0. And that happens, like we saw earlier, when theta is equal to multiples of pi, whole number multiples of pi. And so here let's make one last table. So here, I can't plug in 0, right? 0 leads to an undefined result because if I take cosine of 0 over sine of 0, well, sine of 0 is 0, so we have 1 over 0, we get some undefined quantity, like we sort of expect. And so here, if I plug in pi over 4, well, this is cosine of pi over 4 divided by sine of pi over 4. In other words, it's going to give us the square root of 2 over 2. We get 1. Or actually, no, this is the wrong side. Here's pi over 4, comma 1. Okay, what about pi over 2? Well, here we get cosine of pi over 2, that's 0, over sine of pi over 2, that's 1. So we get 0 out at the end of the day. If I plug in 3 pi over 4, well, what we get is -1, right? So, I mean, you can think of this as a reciprocal of tangent, right? Tangent of 3 pi over 4, that's going to correspond to this angle on the unit circle, that's sloping downwards at a 45-degree angle. Tangent of that angle would be -1, and cotangent is the reciprocal of that, so we get, well, we still get -1. And we kind of get this similar picture to as our tangent function. It looks something like this. And so, tangent of theta, it's going to repeat itself every pi interval, just like our cotangent function is going to repeat itself every pi interval, just like our tangent function. And so we see this graph here. And so the last thing I want to say is that we can identify the range here for our cotangent function as well. And so the range, just like our tangent function, is from negative infinity to positive infinity.